Hey, thanks for having me again. It seems I've said some bad things last lecture because there are definitely less people now here than in the previous session. I'm not even sure which other lecture there is now in the parallel room. Anyway, so I'm taking 30 minutes of Daniel's time for a little intro about geomorphometry, and then I will quickly hand over to you.
All right.
So this is about Julia. And then a little bit about my research. So I talked about generic Julia language use, but my own PhD research is about creating global terrain models. So elevation models using new remote sensing missions, such as ISAT-2 and I've made several packages for that in Julia. One is SpaceLighter to actually process all that data, and one is geomorphometry to basically analyze a terrain model. Such as hydrology, slopes, and I will walk you through that package and just showcase you a few things. So what is geomorphometry? I think it's always good to start with that. We have geo, we have morpho, and metry. So we're basically talking about the quantitative analysis of the shape of the terrain. We're talking about the terrain is the terrain of the Earth, topography. And there are many interesting things you can say about the terrain of the Earth, right? Because elevation, at least for my work, but I think this goes for most models, it's one of the most important data sets you can have because it determines flooding, it determines sea level rise, you can see subsidence, you can use it for landslide susceptibility. For example, this is a photo from Unsplash by Kurt. And this is a bit of an infamous atoll. This is the Bikini Atoll, so it was used for the atomic tests. But these small atolls in the Pacific, with sea level rise, these are completely threatened. And you can only determine that based on very accurate elevation measurements. So hence elevation models. And there are a few differences between, if you talk about the elevation model, you can talk about the DTM, a digital terrain model. And then we're often talking about an elevation model that's been produced using local sources like an airplane or a helicopter. So here's an example of that. This is in Austria. This is based on LiDAR, so LiDAR from an airplane, a 1 meter resolution. So you can see very much detail. You can see individual roads, small ditches, etc. And you don't see forests and buildings here because it's a terrain model. They have been removed from that data set. But this is local. This doesn't scale to the whole world because you need to have a local collection, you need to have a rich country so it can actually publish that data open source. So if you go globally with remote sensing, you go to a radar or optical satellite, the resolution becomes 30 meters. And then we're talking about a surface model, a DSM, a digital surface model, because as you can see in this picture, there's suddenly noise. And one of the noise patches is actually the top of a forest, or at least somewhere in the trees, and the top of buildings. So if I go back to the 1 meter, this one is definitely lower and more detailed than this surface model. And this poses a problem because if you now want to say, I want to see how my water flows, you want to remove the buildings. Otherwise, there are barriers in your flood modeling. And not everywhere in the world. I mean, in the Netherlands, there's a good terrain model available. But if you go to Indonesia, there's no such data. So that's something to keep in the back of your mind. And I think it's the most basic premises of elevation modeling. So how to analyze all of this? Well, we can use a geomorphometry package in Julia. There's packages in Python as well, like XDEM. And for this, I will open the geomorpho IPython notebook from my previous session. It's in the same folder. So that's the OGH repository under my name. And I will walk you through that. But you can follow along if you want. I'm going to switch to my... Hey, where's it gone? Oh. I lost my tab. Crap, I lost my tab. What? There we go. Too many tabs open. So I have here geomorpho.ipnb. And I will show you basically how to open an elevation model. And I think I've seen Yufeng. Are you here? Oh, look, there's Yufeng. Yufeng presented about his improved global elevation model. So it's basically taking a surface model and then trying to correct for the vegetation and buildings, removing that. And he presented that. So let's open that one. We're using the rasters package. Is this, by the way, big enough for everyone also in the back? No? Bigger. Now?
Yeah, more or less.
There's room in front. So we say using rasters, using ArcGDAL, so that's using GDAL on the backend to load this data set. We give this address, which is on the internet, so it's not a local file path, just a URL. And very importantly, we need to say to raster, when we load this, that it needs to be loaded lazily. So lazy is true. Because as you can see, when we load this raster, it is a raster that's 1 million by 540,000 cells. This doesn't fit in the memory of my computer, right? So if I wouldn't have done lazy is true, something would have crashed or something would have become incredibly slow. So that's how you open a raster lazily. So this is only loading the metadata from the internet. So it knows the dimensions, it knows the metadata, didn't pull any of the actual data in. We can check the metadata. There's nothing there. I know that Yufeng is working on adding actual metadata to this file, right? And now let's look at my favorite holiday area in Austria. So let's crop in a small extent that we can actually load in memory. So I'm using the extents package to basically define bounding boxes to define an extent between these latitude and longitude. And then using the crop method, and a bit cheating here, I need to divide by 10 because it's a scaling factor in this TIFF that we're loading. It will be in the metadata in the future, so then it might be automatic, but now we don't, otherwise we don't know now. And then we can plot that. No, we're just reading this into memory, by the way. Oh no, what the hell happened? Okay, now we can plot it. I think my VS Code is trying to save this file at the same time. That was the message. Let's ignore it. This is really the demo effect, right? Trying to plot something and then
Probably.
nothing happens.
It's just pre-compiling. Now here we get.
Okay, so this is an area of Vorarlberg in Austria. You can see some nice details, some mountains, some floodplains, and then clear river channels. I'm using the turbo color map here because it has a very wide range. Maybe it's not the most scientific color range you can take, but it's way better than rainbow. But of course, this doesn't really say much, right? You don't know the height, you don't know how steep stuff is. So there are better ways of visualizing an elevation model. And a very easy one is hill shading. So we can do that. We're going to use the geomorphometry package that I wrote. We can call hill shade. And then you get a very nice error. And I actually talked about this, I think, in a previous lecture, that some of the error messages you can get in Julia can be quite long. But essentially it says, I know there's a hill shade method, but it doesn't apply to this raster. Because I need to, well, what's happening? This raster has no data values in it. And my hill shade method doesn't like that. I should probably implement that. It's on the backlog. So we need to replace all the missing values, the no data values in this raster, and then we can plot it. So we use the function coalesce to do that, to replace missing values, and we're just going to replace everything by the minimum value of this whole elevation model. So when we do that, you get the same raster back, and oh no. And then we can plot the hill shade. I was thinking it's restarting the whole thing again. Okay, so this is a bad demo effect. I'm not sure what it's doing.
ballpark is not defined.
Hmm?
The ballpark is not defined for me, so it stopped there.
Which variable is not defined? Of Wahlberg. Wahlberg, then probably the crop here. Then this probably filled. So probably some cell above filled, and you can try to rerun everything. I had to move on because of time, otherwise Daniel will kill me.
Don't worry.
Anyway, I'm not going to execute cells because it's way too slow. So this is a hill shade, and this is basically simulating a light source, like a lamp, as it were, a small scale model here on the desk. And then you get sort of shadows. It's artificial because if you look at this, the sun is coming from the north. A bit weird. So there's also a thing called multi-hill shades that you can call, and then you can determine the azimuth of the light source. You can specify multiple light sources in it. And then you'll see that in this new plot, there's actually the darkest area is the north side of a steep mountain, which is quite correct. So this is already, I think, a better way of visualizing an elevation map than just plotting height. And we can go one step further. There's a nice method called the progressive slope map. I'm not going to execute cells anymore because it's done that in the past, and otherwise it's too slow. So this is using slope, and it makes slopes really quickly very dark. Basically, as soon as you cannot walk it anymore, it becomes black. And so this is a very human-like map to interpret terrain. And this is used in archaeology, because if you do this on a high-resolution map, you can clearly see terraces and other human-made features. I think the original author also calls it bone mapping. So there's science in visualization. But this is determined by the slope. And you can see that if we actually calculate the slope of an elevation model. It's just a bit of a lighter gray. If you think about slope, though, slope is rise over run, right? And the rise is in meters, because we're talking about elevation model, it's in meters. But as you can see in this plot, we have latitude and longitude. So the run is actually in degrees. But this picture looks pretty all right. So what's happening in the background is that we automatically see that this is in WGS 84, so degrees, and we need to calculate that, convert it to meters, and then we can calculate the correct slope. And that's all happening in the background. So we have an automatic cell size. Oh, it's skipping. So we have a method cell size that operates on this raster, and it actually gives you 20 by minus 30. So that's the actual width and height of the cell. Yeah?
So what projection system is it? It then projected? Because it's automatically, but can we know which CRS it's using then?
Well, it is basically determined from the WGS 84, and it's now using a very simple circular transform, assuming just that each degree is 111 kilometers, and then just taking the cosine of the latitude. I believe that's correct. So it's an approximation. Do I need to stop already?
No.
No.
You're on time.
And this is minus 30 because most of the images are flipped. They go from a cell above to below, so the step size then can become negative. If you would set the cell size, because you can actually, instead of determining it automatically, we can also provide a keyword argument cell size to most methods. If we set it to 1 by 1, you actually see that you get crazy slopes, right? Everything is higher than 80 degrees. So that's clearly incorrect. This is an approximation because we calculate a single cell size. It would actually be more correct to calculate the cell size for each cell in a raster. Because if you have a very large raster spanning multiple degrees, it's actually like this, right? If you plot it on the Earth, you will actually show that probably. Then you should move to DGGS.
Yeah, one use case.
Yeah, one use case. And we can plot that distortion, actually, because if we import proj, then we can actually do correct conversions. We can plot the cell area of this raster. And then you see that the cell area is highest in the south, and above, because you go to the poles, higher latitudes, it becomes smaller, and thus the area of each cell becomes smaller as well. So the automatic cell size is an approximation. Don't use it on a continent. Use it for smaller cutouts. I might, if you wanted, I can make that into this package maybe somewhere in the future if I need it. But of course, you can see that the cell area goes from 645 to 646, so it's negligible at this scale. So these are important things to keep in mind if you want to do operations on geographical rasters. And elevation models, global elevation models, are of course almost always geographic, unless you're using a DGGS. The more reason to use them. And otherwise, it's a source of tricky bugs, wrong answers that you get. So I'm using geomorphometry.gl also to teach myself. So what I like to do for the slope calculation is actually implementing multiple methods from the literature, right? There have been many smart people implementing different ways of calculating slope. You can just say, I'll take the steepest slope. If you look at a cell and then it's 8 neighbors around it, just find the steepest slope. So that's maximum downward gradient. And then there are nice ways of actually doing filling equations and solving them based on all maybe 4 neighbors or even 8 neighbors. And that's basically Zevenbergen, Thorn, and the Horn method. And if you plot these, they're already plotted, you can see that between Zevenbergen, Thorn, and Horn, you don't see it on this scale. If you zoom in, you would see subtle differences, but the maximum downward gradient is actually pretty bad because it just always takes the steepest slope. You get very strict directions. It's not smooth. Well, you can plot the aspects, and if you're plotting aspects because it's 0 to 360 degrees, you're plotting essentially a circle. It's always good to take a circular color map, such as the Roma 0 color map, and you can make nice plots like these. I think if you want to use this package and for the exercises, try to make a very nice visualization, overlapping aspect with slope, and then you can create beautiful maps. Sorry for all the interruptions of my Jupyter notebook. The previous session went way better in terms of the hiccups.
We switched to the other side of the room.
Yeah, this is bad side. So this is aspect. There's also curvature. I won't go into too much detail. There are many forms of curvature. There has been a very nice paper from Minar, who basically inventorized all the possible ways of doing curvature, making a full system of possible ways of calculating it, criticizing all the papers that came before it, and nicely categorizing them. I tried to implement some of them. Other packages have more implementations, but it's always nice to see. So curvature you can do. There's relative position, which is basically taking an elevation cell and looking at its 8 neighbors and determining whether it's higher on average or higher for the absolute values. And if you do that simply, only taking the 8 neighbors into account, it's a way of determining quality of the elevation map. If your elevation map is very noisy, you can see that when you plot it like this. And you can actually see that this global elevation map is a bit noisy. You see a lot of speckle noise. So what you can also do is actually not just take the 8 neighbors. That's called a Moore window. You can take another stencil. We can use the analyses. Set the outer size to 4 and the inner size to 3. And now instead of comparing the center elevation to the average elevation of the 8 neighbors, you take the average of this circular pattern in the raster. So a way bigger window. It will be slower, but if you then plot it, you will see that you get a much stronger effect in terms of relative position. I'm using the same scale here, but also that the noise is mostly gone. So this package has multiple algorithms for most of the functions. So you can compare literature essentially, and you can use different sized windows, depending on your analysis. And then last but not least, I'm still in time, I see, is I've implemented, again skipping, very irritating, I used some hydrology, implement some hydrology methods, mostly flow accumulation, and implemented the D8, the infinity, and the FD8, which is basically only drain water in the steepest direction, so like the maximum downward gradient. Then the infinity basically says water can drain from a cell in 2 directions, but always 2, and we can divide the water based on the slope. And then we have the FD8 method, and it basically says I can drain to all downward cells, so all cells that are lower than my center cell. And of course, you can play with the weights between the distribution between these cells. And if you plot that, you get, well, always very nice patterns. The 8 is very recognizable, and it's used for many hydrological models afterwards because it's quite straightforward. The infinity becomes much nicer because you can see that in the D8 one, water basically only drains in straight directions or diagonal directions. It's not smooth at all. It's very discrete. So this the infinity in the middle already becomes much smoother. And it's actually, I think, doing pretty well. I think most literature uses the infinity by default. And then FD8 becomes, I'd say, even nicer. And you can see clear bifurcations again. D8 basically cannot create bifurcate again or flood a floodplain. It has to go in a single channel. But FD8 is considered by some to be a little bit too much. Because basically, if you would take a cone, a perfect cone, and you would drop water on one side of the cone, you would expect the water to just go straight down, might disperse a little bit. But with FD8, it could actually go in circles around the cone, just because it would, for each cell, it would go in all downward directions. So up to you which method you choose, but it, again, this was very insightful for me when I implemented it. This was also a source of bugs, so if you install this package beginning of the week, I made a new release yesterday fixing bugs in the infinity and FD8. And that's it for geomorphometry. And there's more functions, mostly filter functions, if you want to go from a surface model to a terrain model. There's cost distance functions, and I think that's, oh yeah, and yeah, classification. And I'm still working on this package because I'm still working on my PhD. 1 more year, hopefully. Yeah, that's it. So this is geomorphometry analysis in Julia using the geomorpho.gl package. Any questions about that? Yeah, of course, you think. Yes.
I'm curious about the reprojection on the, it seems like a reprojection on the fly, right? To set the, when you compute everything, you get from this long to meter-based cell size. It's default 111 kilometer, and 111 kilometer is very inaccurate in the sense, right?
Yeah, it is.
And I don't know how the DGGS can probably in the future implement some smash function to actually reproject to the DGGS. Maybe because according to my colleagues, it could be way more accurate to doing the smash, like triangle grid. It is possible in the future that you implement it with the DGGS group with this functionality in your package.
That would be really cool.
Because I don't see any other people have done it before. And also computing large amount of the global Earth, this projection is really hard to adapt to different places of the Earth. So I think it will be a very nice add-on if this kind of functionality can appear.
Yeah, especially when it comes to digital elevation models at global scale.
Yeah.
The discrete global grid system I'm currently developing, it's also just like rasters. It's an array, and I hope maybe in the future it will be compatible with your Julia package, so you can run those plots on it. So the idea of Julia is that it's not just one isolated package, but the packages are compatible against each other, and both your geomorphology package and my package, we are using certain standards so we can interchange our array formats, and I think in the future it might be possible to use it on a DGGS.
Agreed. Maybe with one warning, we had the discussion, I think, during the panel this morning, and I think it's important to know don't always go to the highest resolution, right? There's very stupid simple methods, and they might be wrong most of the time, but they're very fast. And then they're the most correct methods, but they might be slower, right? And so it's the error decreases, but performance also decreases. I think DGS is the most accurate. The question is whether you need it on some raster. So I now choose a sort of middle ground, and maybe we should do formal analysis of the actual error and see how it improves and when it matters.
That's for the, yeah.
And the use case, of course, matters. If you're only interested in for Arlberg, you don't need a DGS.
True that. Okay, thanks. That was it. Daniel, the floor is yours.
Okay, thank you very much. Yeah.
Unmute yourself, please. Yeah.
Let's start with the DGGS intro.
Oh, wait, one thing.
All right. I want to talk about discrete global grid system and how they tessellate the Earth into cells of equal area around the world. Who of you have already attended the DGGS session of Loos in the past days? 1, 2, 3, Loos himself. Okay, makes sense. But it's not everyone, and since I'm introducing a Julia package based on that global grid systems, I just try to give a quick recap about what the DGGS actually is. It's still quite niche. There is less but emergent software to be written, and this is maybe why I just want to start my session as a quick motivation. Of course, there is maps. Maps are two-dimensional. The Earth is not two-dimensional. And if you look into the Mercator projections, the appeared size of Greenland and Africa are almost the same, which is, of course, false. So maps distort our view on the world. And there's always this trade-off between either trying to aim towards an equal area projection or towards an equal angle projection. Like you can get area right, you can get length right, but then you lose some distortions on the angle. So there's a trade-off, and if you're doing this trade-off, you may ask one yourself, like, how to solve this trade-off. Like the distortions, they matter, and it's not only that they matter in terms of visualizations, but also when it comes to modeling. Like when you're doing some deep convolutional neural networks on your maps, the network is also seeing distorted data. And now we want to think like how we can minimize these distortions as best as possible. So one solution would be just use local projections. If you just look into a given area, you just can center your projection based on that location, like for Arlberg we did a couple of minutes ago. Or here Antarctica, it's used quite a lot, and it fixes this area of distortion. However, you cannot see the rest of the Earth. So another solution might be to use multiple projections instead. So there is this UTM system around since World War II. People are tessellating the Earth into multiple zones. They are centering their projections based on their zones. And this is also basically what is used in Sentinel-2 data. However, those zones are not rectangles, but your cog files are rectangles. And this yields to an overlap. When we have two different nearby zones and we want to access data, some locations are being present in neighboring tiles. And this yields into about 30% of the data that is duplicated, and that needs to be stored, needs to be downloaded, and also needs to be processed. So discrete global grid systems try to minimize the data by providing some lossless compression, so we do not need to download so much data. These principle of distortions exist not only in Sentinel but also in Landsat data. But depending on how you make your tiles, you might get slightly different distortions. And there's once again this trade-off between either being equal area or equal angle. So analog paper maps, they force us to make two-dimensional maps. Digital data, however, it's most flexible. We don't need just a plane. We can use arrays of multiple dimensions. And one solution is to use polyhedrons, like the truncated icosahedron here as a reference system to tessellate the Earth instead. So like this UTM projection, instead of having one global projection, we're having 20 local projections in this case. And since we are just using the polyhedron, which is flat, we do not have those overlaps of overlapping Sentinel-2 tiles anymore. So examples of applications of those approaches using polyhedra in the past might be the icon grid from the German Weather Service, using an icohedron and great circles to tessellate the Earth into equal area cells. And you can use this recursively, so you have bigger triangles, and you can make by cutting the half of each side to make it even finer and finer spatial refinement levels. And similar approaches have been used, for instance, by Google GraphFirst or the AIFS model from ECMWF. Here we also see that there is a icosahedron involved. However, those models are optimized for modeling, where the bottleneck is the compute. In Earth observation, especially if you want to process satellite images, our bottleneck is usually not the compute, but the loading of the data. And we need to deal with projections, and our resolutions are much higher. We need to process much more data. So we need to talk about projections and data structures. Entering discrete global grid systems, which take this idea of using a polyhedron, which is having flat faces, as a representation for the Earth, adding a projection and an index to it to have an efficient data structure for high-resolution satellite imagery. So we try to not wasting so many petabytes of data by having a seamless tessellation of the Earth. And this helps us also when it comes to train models in machine learning aspects, because those data that needs to be loaded also needs to be decoded and prepared in the GPU, and the less data we have in our input, the faster we are also in training. DGGS are standardized. There's an ISO standard, there's standards from OGC, and people know what this DGGS actually is, what they should mean. However, the current bottleneck is like building actual software that uses those definitions in order to make tools to process the data in a DGGS. You can use DGGS in multiple fields, like in ESA soil moisture and ocean salinity mission. For instance, DGGS is used in their level 1 sea data, not because they like polyhedrons, but because the way how they put the geometry of the sensor, which reassembles a hexagon, which can be used as a pixel shape for the DGGS. Another thing is, like, it's not a grid system. It's not a grid it's a grid system. So we have different spatial refinement levels, and this is why it's also being used in integrating multiple data sets at different spatial resolutions, like here in flood mapping, or when it comes to integrate both raster and vector data. So DGGS, sometimes people say that it's kind of like a hybrid. It sits in the middle between raster and vector data, and you can use the system to index both types of data sets. So when you want to build a discrete global grid system, you can pick from different polyhedron, different cell or pixel shapes to create your final reference system. Then there's something called aperture, which defines you like the next spatial resolution, how many pixels per do you need to aggregate to the next Corsa resolution. This is some value you might be able to pick depending on the polygon you choose. And then we need to index array, like naming all of these cells, how to go from cell 1 to 2, and so on and so forth, in an efficient way to use it for processing and visualization of data sets. There has been some DGGS software implementations being made. One of them most prominent might be H3 from Uber or S2 from Google. And then we have this DGGrid library, which is more focused on precision of hexagonal grids, as like other discrete global grid systems having diamonds or triangles. So in the past, we had all our grid definitions. We have tools to transform between geographical coordinates into cell IDs and vice versa. This is what the H3 library currently provides us. Now we can select appropriate discrete global grid system, and now we actually really want to develop some tools to build and work with so-called DGGS native raster data cubes. The difference between a normal data cube, where you have longitude and latitude, is just like you have a different spatial dimensions, like a cell ID. That's the only difference between raster data cubes in the traditional world and DGGS data cubes. The only thing that we change is space. Everything else, like time or the band, is still the same. So at the end, we can still use packages like XArray, we can use ZAR, NetCDF, whatsoever. We just have arrays with labeled dimensions, and this is what we can use as a data structure to store DGGS data natively. And it turned out that if you compare different discrete global grid systems, that if you use this Snyder equal area projection, you're really good when it comes to this equal area part of DGGS. And if you use hexagons, you are good when it comes to compactness, which is related to angular distortion. So this is what I used to start my discrete global grid system in Julia. And then I found out that hexagons are way too hard to implement, and I just started to using diamonds instead, because then it's much faster. But in theory, basically, maybe in the future, we will have hexagons as well in Julia. So why hexagons? Hexagons represents neighbors. Like imagine you're having a triangular grid and you want to just calculate the distance between a center cell and its neighbors. You might have different types of neighbors with different lengths. This is something you also have in diamond grids or square grids, but this is a nice feature in hexagonal grids, where basically the distance between a center and a neighbor is always the same. So this is my motivation to extend the Julia package in the future. But let's start with the Julia package itself, using data cubes
to do slideshow.
Yes. All right, so this is discrete global grid systems, and now I want to motivate how to do data cubes in discrete global grid systems. Are there so far any questions regarding discrete global grid systems in general? All right. Yeah, Luis?
I have a question, which I should know, but I don't. What is the projection used by Google in S2? You have a reference there to something?
Yeah, I think it's, so Google uses a cube. And then we need to look it up. Uber H3 uses the gnomonic projection, which is neither equal area nor equal shape. I think due to the fact that you're using a cube instead of a platonic solid having even more faces, I would assume that the distortions in Google S2 is even higher. But we can still look it up. All right.
And what are you using in Grass?
So Grass doesn't have DGGS.
Oh.
That's conversation for a moment.
All right, so let's talk data cubes. I like to start with this nice comic from Development Seed I found about a story of a guy who wants to help scientists to find the best data format. Look, we are getting a signal from some new scientists now, and the scientist is asking, we are trying to understand mangrove deforestation. We hope we can help us with our data. So the Sentinel-2 satellite products are high in spatial resolution, and they are using COG files because it's raster data. Another story is not about satellite images, but about smoke plumes. So here someone wants to know where the smoke of a volcano will go, and there is some bounding box being presented in the plume, and here they don't use COG files, but they're using GeoParket because it's this vector data where you can basically store only the points of the boundary of that plume. So in theory, you can also use a raster to store your plume data. But then there's lots of missing data because it's just a local event. So the question here is, which story fits best within a discrete global grid system data cube? So if you want to work with raster data, and we are just we are just having a use case where we want to store the bounding box of a plume, do we need a DGGS for this? Or don't we? Like, if you just have a couple of points of a city, and you have a city, then there's some house burning. Do you need a DGGS for this?
No.
Right. Okay. So some use cases might profit from DGGS, others don't. So we are working with data cubes. That's a data cube. It has cells, and those cells has dimensions. We can label those dimensions, and for each combination of longitude, latitude, and time, we have some value, and the value has the same type. So this is just a data cube. And we can store those data cubes using various formats, including ZAR, COG, or NetCDF. The thing is that under the hood, they are more or less the same. Because they're using this Unidata's common data model. They are just arrays with dimensions. So if I'm talking about array, I'm meaning that I measure the temperature for all possible combinations of time and space. So then this reassembles to a cube, and this is an array. And maybe I have a digital elevation model. Which is maybe constant over time. So I have some height data for every longitude and latitude, but not only just one time point, and then I can just add it, align it to that data cube. So sometimes the width is the same, but the height and the depth might differ. So you have arrays, and those arrays can be aligned. And a set of arrays that can be aligned is called a data set. So a data cube actually is not a cube, but a hyperdata cuboid. Like a cube is something where the length is the same and it's three-dimensional, right? You don't need to have latitude, longitude, and time. Sometimes there is other variables as well, like the band, for instance. So it doesn't need to be three-dimensional. It can be any dimension. And the only thing that matters is that those arrays have labeled dimensions, like the x-ticks, like this is the longitude 180 and so on and so forth. And you don't need to label every individual cell, you just need to label the dimensions because they're in a grid. So you don't need to store the metadata for every cell. And that's the point of using a raster instead of vector data. You don't need to repeat the metadata for every cell. And in machine learning, this thing usually is called tensor, like matrices or vectors. And once you have those data set with axis labels, you call it a data cube. So in the Unidata model, you have kind of like a file structure with groups and subgroups. And in those subgroups, you might have files, and those files are the arrays. And you have dimensions that define you how many points you have, how many time points, for instance, or how many spatial cells. But in the Unidata common data model itself, there is no date, there is no units, and there is no tick labels. And this is where climate forecasting conventions comes into place. So when I talk about data cube, I do not only talk about this data model, but I also implicitly tell you that I'm using this climate forecasting conventions. Also for DGGS, because this is how we add metadata like names, units, and tick labels. So you can do this manually, and you can also do this using packages. So this is a data cube, but on the other side you have data frames like geodata frames. And this is basically where you are storing every point, every cell, line by line, using vector data. So on one hand, you have this sparse data frame, and on the other hand, you have a dense data cube where you have values for all possible combinations. And our DGGS package is focused on dense data cubes. It's not working, not used for data frames. So this is why we are using arrays and not just simple tables. So if you just want to do this in Python, you have pandas and xarray. And if you want to use it in Julia, you have data frames or Yax arrays instead. So Yax array is a Julia package, which is the equivalent of xarray and in Julia, currently implemented in our institute. And this is basically the package I'm using to build the DGGS data cubes on top. Task and xarrays is a generic way to parallelize computations based on any collections. You can use Dask for sets and data cubes and everything. And the reason why we developed a Yax array is because besides sets, the data cubes are aligned, like they share dimensions of space and time. And this is why there's efficient ways in order to execute those plans. So Dask is a very generic library for parallelization, and Yax array is a specific parallelization engine just for aligned data cubes. So we developed DGGS.jl, which is Discrete Global Grid System for Julia. And now I'd like you to show some examples on how to use it and how to convert geographical data into DGGS and back. And the way how it's done is that if you are starting from a globe with longitudes and latitudes, and you choose a DGGS based on an icosahedron, you are tessellating the Earth into 20 different triangular faces. And this is one of them. And the idea of a data cube is something rectangular, right? The angle inside of a cube is not something like this, it's always 90 degrees. So we need to make matrices out of it. So the whole idea about the index of a DGGS in our package is how to go from this to something with rows and columns. Because once it has rows and columns, we can store it efficiently. So we are starting with the icosahedral Snyder equal area projection, yielding us points on a plane. But this still doesn't look like matrices. So what we did after that is to apply a transformation of a skew and a rotation, yielding 5 different matrices. So the way how we number our cells is such a way that we can store our entire raster data sets into 5 different matrices. So our final DGGS spatial dimensions are not 2, it's not longitude and latitude, it's 3-dimensional. Here we have a 3-dimensional space index. We use the row, the column, and the number of the matrix. So whenever you are talking about cell IDs internally, it's basically ordinate system, 3 numbers, telling us the row, the number, and the matrix, and these combined is basically the cell number. So we can just aggregate all of this number together. We're writing the bits of n, and then we can add the bits of j, and so on and so forth. And then we just have one number, and this is what we need to be OGC compliant. So either you have just one number, or you have 3 numbers, and you can convert between those back and forth. But the only really important step here is like we need to find a way how to store all of this pixels, all of these cells in rows and columns. And if we define those array, then we can use it to create our data cubes. So, yeah.
Can I ask something now?
All right.
So, Jérôme Sonville from DGGS does something similar. Are you aware of his work, or?
Sure.
It looks very similar. Do you know if it's even the same?
Yeah, at Living Planet, we talked about how to go from latitude and longitude to rows and columns. And he also came up with similar idea, but the only difference is that I think the orientation of the matrices. So this is not a final standard yet. This is just a way to show you that you can create data cubes on a discrete global grid. Once we agreed on, let's say, do we do the rotation clockwise or counterclockwise, then we can set it, and then we can process this on big data sets. So up to now, I just converted a single Sentinel-2 tile into a DGGS. And once we want to scale this approach, we need to fix like whether we want to go clockwise or counterclockwise. But the principle is the same. Okay, where's my...
Minimize this one.
Okay.
You left the meeting.
Oh.
Oh, no.
Maarten, can you please?
Yeah.
I'm not a Mac user.
Died.
Oh, okay.
Oh. You can try to connect to this one. It looks kind of okay for now.
Oh, we still have battery left. We're back on Expert Street.
Okay.
Where the hell is? Oh, you minimize this, right?
Yeah.
Yeah. Can you please minimize yourself?
Hi.
Yeah, 3 dots. 3 dots on your screen there.
This one?
On here, on your screen, 3 dots.
Oh, that one.
Yeah,
Wow.
and minimize. Yeah, thank you.
We're presenting, so we're back in business.
Yes.
We'll switch. And then we'll make this a bit bigger.
Yeah.
Okay, everything fine?
Yeah, thank you.
All right. So this package is already public. It's on GitHub, and you can find it by just Googling DGGS.jl. And this is basically just part of the documentation containing some tutorials about how to deal with those DGGS datasets. And this is not a Jupyter notebook. This is just HTML where you can see the results. So if you click on Get Started, you can install those Julia package by typing package.add. Keep in mind that this is...
Can you please zoom in?
Sure, okay. Control.
Commands plus.
Is this big enough for everyone? All right. So in Julia, there is this package manager where you just need to type add and then the name. This package is not yet registered. So instead of typing the name, you can also just add the URL instead. So if you want to go to the leading edge of some package developments with Julia Package Manager, you can always use the GitHub URL, and then you're just on the latest commit if you just want to try things out. And the most easiest, the most basic thing to do basically is to convert between latitude and longitude to those cell IDs. And there's the function called toCell. Then you can just put your lat and long in there. And then you also need another number called resolution, defining your spatial refinement level. So it's a grid system. We have different grids at different spatial resolutions. And depending on how big the number, the resolution number is, your 1 out of 5 matrices might be bigger. So if we go to the data format once again, in a coarse-grained, low-resolution data cube, basically this would be a 4x8 matrix. If we go 1 spatial resolution up, this is not 4x8, but 8x16. So the way how we increase the resolution, the precision of those cell IDs is by just multiplying the rows and the columns by 2. So we can convert between latitude and longitude, yielding our 3 numbers, which is the number of the matrix and the row and the column number. And of course, we can convert it back to have values that are similar to the input values, but not exactly. It's not a continuous grid system, it's a discrete grid system. And this basically is not the exact point of latitude and longitude. This is the center of the cell in which the corresponding point is sitting in. So if you have a very high resolution, this conversion back and forth would give you pretty much the same numbers. If you have a very low spatial resolution, there might be some errors. And this is because of the discrete part of discrete global grid systems. So usually you just do not want to convert the coordinates, but just use actual data. So you can use the YAX-array package to create an array with spatial dimensions very similar to every one of us, namely latitude and longitude. And this looks pretty much like the geomorphology package where Maarten introduced the rasters package. And this is because the YAX-array and the rasters of and the raster of rasters JL basically is a very similar type in Julia. So you don't need to use a YAX-array, you can also use a rasters to interface with our package. So this is just data in lat long. We can plot this data in lat long. Nothing serious, everything is fine. But now we can convert this lat long data into what is called the DGGS pyramid. It's a grid system, a system of grids at different spatial resolutions. And this is why the result here is not just an array, but a sequence of arrays. So you start with the highest spatial resolution, which is an array 32 times 16 times 5. So every array is always 5 matrices. And if you want to go to a coarser resolution, basically you're just halving the number of rows and columns. So this is basically pretty similar to an image pyramid of GeoTIFF files, but not based on lat long pixels, but in the DGGS space. And this is also what is being used when it comes to visualization of the data. If you don't want to zoom in, if you just want to have a quick overview about the globe, you do not access all of the high resolution data. You can just access lower spatial resolutions, which is pretty similar than the overviews. Another thing is that besides those set of arrays, we have some other metadata here, which is the discrete global grid system reference system. So depending on how you define the ray, how to go from latitude and longitude to cell ID, there's different ways like S2, H3, and so on and so forth, doing counterclockwise rotation, clockwise rotation. So this is why every discrete global grid system also needs an identifier to know how to go from coordinates to cell ID and vice versa. Another thing is that we also save the bounding box in geographical coordinates to know what part of the Earth we are currently covering. So if we have a pyramid, we can access certain layers, like this is the third spatial refining layer, and then there's probably multiple bands or layers are they called here. Since it's just one array with one variable, we do not have red, green, and blue, we just have layer 1, but we could have. But if we just say, okay, this is our pyramid at that given resolution, we want to select the band called layer 1, we're yielding not with a pyramid, but just with an array. And this is like rasters, but the only difference is that instead of X and Y, we have our 3 different DGGS spatial dimensions. This is something we can also plot. And this is interesting because here we see the discrete part of discrete global grid system again. Like here you can see all of these tiny diamonds, and those are the bounding boxes of the cells of the DGGS pixels. Not in DGGS space, but reprojected in lat long. So whenever you do some plotting, the software will automatically reconvert it back to lat long, and here you see those areas. You might wonder why some of those cells might be much bigger than others. I was promising you an equal area projection. However, we just redo it, and now we are seeing everything based in plat carré lat long again. So basically, an equal area projection in that space would result into different cell shapes. Like here we have the poles, and of course, in the poles, the appeared area is much higher compared to ones being next to the equator. So it's a little bit stupid to plot DGGS data in such a long space. This is why we also developed a web app called DGGS Explorer. So here, for instance, you see the data not in plat carré, but on a globe projection. And you can zoom in to some data sets. Let's go to Kattegat, Skagerrak, Denmark, next to the coast of Sweden, Gothenburg. And depending on the Wi-Fi, there will be higher spatial resolutions being created on the fly. And now we see something interesting. There's a point. There's some area where we have our DGGS zones. They're pointing towards this direction. And here we have another cell shape. So this is how to spot DGGS data. It's not that every pixel is the same shape. It's like here we have a different cell shape. Why do we have a different cell shape here? Because this is the point of origin, the center of the universe in this discrete global grid system reference system. Here we have a different matrix. Here we have a different phase of the icosahedron. So in a DGGS, we do not have overlapping tiles in which all pixels are arranged in the same way. Here, the shape, the orientation of the pixels of the individual zones or cells are different. But this is just an artifact next to the 12 corners of the icosahedron. So this is just a random planet with random DGGS data.
Daniel, I have a question about DGGS Explorer. Is it using the pyramids as you zoom in?
It's using the pyramids. This is why it's faster if you're using a faster Wi-Fi. And this is also why we are using a discrete global grid system, like normal pyramids in GeoTIFF. Here we have our DGGS pyramids. And depending on the level, depending on the zoom level, we access indeed aggregated data. So this is how to do it on a web browser. And we did it because we know that not every one of us is speaking Julia. So the idea of discrete global grid systems in Julia is like we write the code because we are too dumb to code it in C++. So we need to find some abstraction layer, some language that is easier to write high performance code. This is why we choose Julia. And this basically is using the Julia package, and it's a web server in Julia. And now you can just use your browser to access the DGGS data cubes without the need to install dggs.jl. And it's not only the browser that can display the data, it can be also imported in QGIS. Like what it's done under the hood, it's just providing an XYZ Slippy Maps tile service. This is pretty similar to how OpenStreetMap is providing its data. And this is something that you can copy paste into your QGIS, add a new layer, and then you can integrate your DGGS data cubes natively into QGIS. And this is not like I have the tiles being generated somewhere on my hard disk. These tiles are generated on the fly. Like I save the third of the data, and once the server is accessing some tile, I will paint your tile for you, and then they will be shipped towards QGIS. So this is why it's currently a little bit slower than just using OpenStreetMap in QGIS, because the tiles are generated on the fly. And if you are not a human but a computer, you can also access the metadata in JSON format. This is another data set, which is a Sentinel-2 tile. So here I used RGB bands of Sentinel-2 and converted into a DGGS. Unfortunately, the package currently is not able to combine different tiles from Sentinel-2. So my current work is to convert multiple tiles of Sentinel-2 converted into one DGGS. And I hope that in the next month, we will also have data from the Netherlands, of course, and all of the other data. This is just a proof of work that we can convert some Sentinel-2 data within a DGGS data cube at 10-meter spatial resolution. Let's zoom in to some island. Let's wait. All right. Okay, this is DGGS data at 10-meter resolution, or roughly 10 meter. There's a house, there's a beach, there's pixels. This is Sentinel-2 data. So how to do this? We just convert the raster and call this to DGGS pyramid function. The data can be not only accessed using the DGGS Explorer, it can be also accessed using DGGS Julia package. Like at the end, it's just a ZAR file. We can basically just click on it. And I abused GitHub to store this example data set so we can see through the individual files. So this is a DGGS raster data cube, and it's nothing else than a ZAR store. So for each spatial refinement level, you have a folder. And if you click on a folder, here you have your arrays. This is the data for the blue band. This is the data for the green band, and so on and so forth. And the only thing that is different between a lat-long ZAR data cube and a DGGS ZAR data cube is that there's some additional attributes. Like if you click on this file, you see that the DGGS resolution and the DGGS reference system is just attributes within that ZAR store. So this is just ZAR. This is not Julia. This is something you can open in X-array in Python. This is something you can open in R stars as well. The only thing is that you need to ways to plot this data, and this is what can be currently only done using either the web interface or the Julia package. So this is how to visualize data. And in Julia, you just use the plot function, and then you select the bands. In the first example, we had just one layer. Now we have 3 layers, red, green, and blue. Like if you do OpenGeoHub pyramid on this ZAR data cube, we have multiple bands. True color. All right, so let's do something like computation, calculating the NDVI. So if you open a DGGS, if you open a geographic data set, this is just a TIFF file, in some projected space. You can convert it into a DGGS data set which is a DGGS pyramid at a given resolution. So you have an array. An array is just one variable, like red, green, blue, a band. The data set is a set of bands, and the pyramid is basically data sets for all subsequent spatial refinement levels. So if you just need a discrete global grid and not a discrete global grid system, you can just omit the step of creating the pyramids. So here we have a data set with layers red and near infrared. And then we can do computations like subtraction, addition, or division. So if we apply the scale factor, we have values ranging from 0 to 1, and then we can do this add macro, add dot macro, which is basically telling Julia to apply this specific function to all elements of this array. And this is not DGGS specific. This can be done with any data cube. And then it will calculate the NDVI of every cell. So the result is just one layer. And we can plot it. And we can see that there's a river. The river doesn't have so much high values of NDVI. And here we have some irrigation, some farms. And there's a high NDVI. So there's much more greenness here. So this is how to do some computations based on DGGS raster data cubes. We can also use netcdf files instead of TIFF files. So there's this example file about the fluxes, about air temperature and eastward wind. This is a similar data set, but not TIFF, but netcdf. You can open it as an array data set. You can plot it. This is the temperature at the first time step. And what is different here is that this is a climate data set and not an Earth observation data set, so they put their origin at a different place. This is a nice map if you are interested in the Pacific, but this is not that long as we go from -180 to 180. So here we need to convert this in order to make DGGS.jl understand how to go to lat long using this coordinate reference system. So we can shift the longitude, create a new data set, and then we can convert it to a DGGS. And then we can plot it. Long story short, this is just to demonstrate that you can not only use GeoTIFF, but also netcdf to convert it to a DGGS data cube. All right, so this is my quick tutorial about discrete global grid systems in Julia. I hope I didn't overwhelm you too much. In case you have any questions, just let me know. We still have a couple of minutes.